Hey everyone, so in this video, we're going to do just a short video here talking a little bit about normal modes. Okay, we talked about vibrations for molecules and their selection rules for regular absorption emission spectra and for Raman spectra, right? But we also should just kind of talk about how we describe these vibrational motions for the molecules. Okay, right, so if I have some molecule, right, there's a total of 3n coordinates that it can have, right? There are x, y, z coordinates for each atom in that molecule, right? Well, 3 of those degrees of freedom, right, 3 of those coordinates can be related with just the translational motion of the molecule, right? If all of those x, y, z coordinates move the same amount in one direction, right, that's just translational motion of the center of mass of this molecule, right? And for nonlinear molecules, 3 of those movements have to do with rotations around a certain axis, right? And for a linear molecule, it's just 2 moments, right? Because there's one axis that molecule doesn't really have any mass to rotate around, right? So there's not really 3 rotational axes, kind of just 2 for a linear molecule, right? And so the total number of vibrational modes that the molecule has is related with the 3n number of coordinates that the molecule has minus 6 or 3n minus 5 for nonlinear linear molecules, right? And so those are the total different number of unique vibrations that a molecule can undergo, okay? These are considered kind of orthogonal vibrations, right? We talked about for rotations, right? We define these rotational axes, right? The a-axis, the b-axis, right? And the c-axis, okay? That are all orthogonal to each other, right? They're perpendicular to each other, right? And they're unique from each other. And there's 3 unique axes that you can define for your molecule for its rotation, right? Well, I can define 3n minus 6 or 3n minus 5 unique vibrations for a molecule, okay? And those unique vibrations are referred to as its vibrational modes, or its normal modes, I should say, right? Not vibrational, but its normal modes. So these normal modes are these 3n minus 6 or 3n minus 5 vibrational modes that are unique from each other. If you cause, right, if you enhance the vibration in one mode, it does not impact the amount you're vibrating in a different mode, okay? So these are orthogonal, they're unique from each other, right? So for example, right, I have this, again, CO2 molecule here, right? For the CO2 molecule, I could do these 2 vibrations that are plotted up top here, right, where I could be vibrating my bond between this carbon and this oxygen, or I could be vibrating my bond between this carbon and this oxygen, right? But when I do this vibration, right, I'm going to move the carbon to the right, which is going to change the bond distance, right? I'll call it R2 here, and this is R1, right? The bond distance R2 will change due to enhancing or reducing the amount of vibration in that left bond, right? So these normal modes are not typically a single diatomic vibration, right? Vibration between one atom and another, right? A lot of times it includes a collective motion of many atoms, right? Because again, if I look at the vibration in this bond here, right, it's going to cause a vibration in the other bond, right, which is not then a unique vibration. It's not kind of an orthogonal vibration, right? And so my normal modes are defined, say, for example, down in the bottom picture here, right, where this first normal mode has the bonds stretching and compressing equally for the CO bonds, right? And then the other normal mode is when I have one CO bond compressing while the other CO bond is lengthening, right? And I can move, right, like I can do this joint compression and expansion, right, of the bond, right, the top normal mode, right? I can do that motion and it will never, right, add any amount of energy to this asymmetric vibration, right? These are unique types of vibrations. They're not coupled together whatsoever, right? So another way to kind of say these, talk about these normal modes is they are uncoupled vibrations, okay, right? While the vibrational modes in this top picture here, right, those are coupled vibrations. If I enhance one, I'm impacting the other, okay? But for these normal modes, they're uncoupled vibrations. They're independent of each other, okay? And again, each normal mode has its own vibrational frequency, right? And each normal mode then can be independently excited, right? Now, it doesn't mean that every single vibration in the molecule is IR active, right? Or Raman active, right? That's something we have to figure out, okay? But each one would have its own peak if it has the ability to absorb or emit light, right? So a couple of other notes, right, is if a molecule has an inversion symmetry, it will satisfy what's called the exclusion rule, right? Meaning if the vibration is IR active, it will not be Raman active as well, okay? Inversion symmetry is, you know, a molecule like, right, let's say, yeah, something like just H2, 2 hydrogens, right? If I take the coordinates of one hydrogen and invert it through the center, right, it'll end up at the other hydrogen, right, and the molecule looks the exact same, okay? So there's inversion symmetry. If your molecule has inversion symmetry, then a given vibrational mode is either Raman active or IR active, but never both. Could be neither, right, but it can never be both, okay? Right, and the selection rules, right, for these normal modes and things like that are the exact same as kind of the selection rules we've been talking about, right, for diatomics and other things in previous videos, okay? Right, there's just for a molecule with 3n-6 vibrations, right, there can be up to 3n-6 peaks in that IR spectrum, right? There might not be that many peaks, but there could be up to that many peaks corresponding to those different vibrational modes, okay? Right, so quick question to finish this discussion up, right? How many normal modes does benzene have, right? So benzene has a total of 12 atoms, right? So it has a total of then 36, right, types of motions, if you will, right? And the number of vibrational modes is at 36 minus 6 because there's 3 translational and 3 rotational motions. So there's a total of 30 vibrational modes, right, or 30 normal modes that benzene has, okay? Now again, if you were to take an IR spectrum of benzene, you will not see 30 peaks because not all of those vibrations are IR active.